Professor Hamed Tabki is an assistant professor of computer engineering at UNC Charlotte. His research interest is bringing recent advances in machine learning and AI to enhance safety and health and overall well-being of our communities. And his research has been supported by multiple federal agencies, including NSF Cyber Physical Systems and Smart Connected Communities programs. Professor Omid Shogli is an assistant professor in the Department of Civil Engineering, Technology, and Construction Management at UNC Charlotte. His research is focused on predictive analytics using advanced machine learning, real-time highway safety systems, and decision optimization. And he's involved in several research projects sponsored by NSF, Leidos, Virginia Department of Transportation, and North Carolina Department of Transportation. So without further ado, please take it away. Thanks for coming today.
Hello, everyone. Thanks for the introduction. We are delighted to be here virtually and present our research. As mentioned, feel free to ask questions during the presentation. We would love to keep this presentation as interactive as possible. So the topic we chose for this presentation is toward smart highway work zones, when highway workers meet AI, artificial intelligence, and AR, augmented reality. So this project has been supported by National Science Foundation, CPS program, and it's a collaboration between my research lab, Texar, and SIAM Research Lab. I believe it's one of the first NSF-funded projects that tried to bring artificial intelligence to address highway work zone safeties, which is a big challenge. But generally, in recent years and with deep learning revolution and invent of many advanced cyber physical systems, we see a proliferation of AI in many different applications. And I believe still we are at a very, very early stages and scratching the surface of broad range of applications, especially CPS applications that can benefit from artificial intelligence. We are moving towards smart transportation, smart traffic management, public safety, which I actually have a different project thinking about how we can use artificial intelligence to enhance public safety. And obviously, when we talk about the CPS, it's not just sensing and processing the information. Also, we need to deeply think about methods to bring this information back to the general public or user. So user experience is very important. We believe, and one of the reasons that this research is funded, and a significant portion of this research is not just, hey, this is the next cool AI we have. It's more about, okay, how we can bring the existing invention and advances in AI to the people, giving them a seamless user experience and addressing their concerns from privacy to reliability. So while my research lab and Omid's research lab, we broadly active in these general areas with different research findings for different applications, in this presentation, in this specific project, we're gonna focus on highway work zones that kind of abandoned and is not area that many researchers focusing on. So we are very happy to also have this connection with Samiha and Khan from NYU, and seeing that they are working in a very similar research area. It's very exciting to see colleagues identifying similar problems and trying to solve it, perhaps from different perspective. Just why highway work zones and why safety is important in highway work zones. Actually, it's one of the most dangerous work spaces in US. The number that we have, and I'm sure there are more numbers out there, in 2016, based on the FHWA report, total of 158,000 crashes happened around work zones, which result in 42,000 injuries and 687 fatalities. So not only we observe actual intrusion to the highway work zones that can jeopardize the life of the highway workers as well as the drivers. Also, we see due to the changes in the lane or structure of the highway, that increase the probability of the accidents and crashes. So it's a very important problem. If we are talking about highway safety, I think work zones, both from perspective of enhancing the workers' safety as well as the drivers near work zone are very important. In this particular work, we are primarily focusing on worker safety. However, the driver safety is also very important, and we do believe that there are abundant of research that try to think about innovative approaches from self-driving car to many other augmented reality-based approaches to enhance the driver's perception in highways. In summary, the aim of this project is to create a working in the loop safety system that can detect hazardous or high-risk driving behaviors in real time near the work zones using the more advanced artificial intelligence techniques, and then provide this real-time feedback to the workers and notify them ahead of time, even few seconds or 100 milliseconds before intrusion, so they have more chance to do the proper action. So basically, and this is the promise of AI, not just in this field, in many other fields, how we can move from existing reactive systems to more proactive system, from healthcare to public safety to transportation safety and workzone safety, because most of the technology right now, they only provide alarm to the workers when the intrusion is actually about to happen or is happening. However, our aim is to provide hopefully a few more seconds to workers to have a more chance to do the proper action and hopefully reducing the fatalities. And obviously, some aspects of our technology can be used for notifying and alarming drivers about their reckless behaviors or for any reason if they don't see the work zone. So this is a basic visualization of what we have in our mind. The basic idea is that when we talk about the highway work zones, we just don't mean construction or maintenance. In this case, even we see state troopers and police officers as a short-term highway work zone, because they gonna pull over a car, and they would be there for a few minutes or half an hour or 1 hour. So anything that result potentially in changing the number of lanes in a highway or uh, potentially create some sort of obstruction or result in some sort of maneuver, additional maneuver beyond the normal highway traffic. In this context, we consider it as a work zone. And obviously, construction and maintenance is very important as well. We see in, uh, let's say in the bottom, we see a maintenance crew, let's say just trying to inspect part of the highway, and that result in the short-term highway work zone as well. However, again, the principles that we are proposing here would not be just bonded to the short terms, can be used for the temporary work zones or more long-term and permanent work zones as well. Uh, Again, the idea here is that we can have a camera with the AI board that can look at the incoming traffic and then provide a real-time notification to the workers that are in the work zone. And this notification, what we are very excited and interested about is multimodal inherently. Basically, we provide visual notification plus audio notification. So audio has been explored with some researchers, but I think we are also the first that try to look at the visual notification. And hopefully with more advances in augmented reality, this is the time to think about how we can enhance the visual perception of human workers in a broad range of applications, and in this case works on safety, and some researchers are exploring that in construction safety as well. uh, so that's the core idea. So we have three elements: AI processing, real time on the edge, a local wireless communication that needs to be reliable and low latency, and wearable devices combined with the, in particular, augmented reality glasses to enhance the worker perception. So it's not a system that just designing an AI in isolation, it's more coupling the AI and augmented reality to see how we can enhance the cognitive perception of the workers. And again, many of these principles can be used for many other sectors as well. And I think these are very interesting research areas that open a whole new set of applications. And we are very excited. And in the rest of this talk, basically, we're gonna discuss some of the approaches that we have already taken and some of the early results that we have in each part, and then also some challenges and future directions. So I will cover the real-time AI for vehicle detection, classification, trajectory analysis, and even risk estimation. And then you want to do a risk assessment as well. What is the likelihood of intrusion, as well as the real-time, reliable, low latency communication. And my colleague and my friend, Dr. Shogli, gonna discuss a very important aspect of this research, which is what is the best mechanism to bring back the information to the workers, what is the user or workers experience, and how we can address their challenges and concerns. Again, I'm a solo speaker right now. Feel free to ask questions. Otherwise, I'm going to continue the presentation with the first part. So to show you guys what we have so far, I'm gonna play a video demo of our technology. Again, uh, to create this video, we are working with the industry, work zone industry and highway work zone industry. So they gave us one video example of a hypothetical, highway short zone. And let's just play the video. So we are not doing something really crazy, but the important part is that we are already able, and thanks to so many advances in deep learning, you can think about basic YOLO can detect cars, and in this case, but what we try to do is that how we can make sure that we are detecting cars in from distance. That's very important. And then not only we detecting the cars, we can re-identify them, and then we can also measure their distance. So this is the core part of our AI side that has been developed and is kind of presentable, but obviously this would not be enough, right? If again, the vehicle detection is commodity, right? So everybody can do it. The challenge is that how we can create and classify from distance over different vehicle types and then re-identify them. But after that, still, you have so many questions. So what is the future path? What is the trajectory? What is the likelihood of intrusion? How can I predict whether the intrusion can happen or not? That these are the aspects that we are seeking to address and find answer for. But let's start with what we developed so far, which is pretty standard. The core kernel is vehicle detection and classification. So we need to localize the vehicles and classify them for that. And again, I don't want to go deep into the AI technical part, but I would be more than happy if you guys want to if you have a specific question, or you can follow up with me later on after this presentation, is that we have a backend classical convolutional layer similar to what you can find in mobile net or efficient net, and then we have a hierarchical neck structure similar to what you can find in the efficient net, or I would say that in YOLO is very YOLO-ish kind of architecture, with the head that is more customized just for highways and vehicle classification. So we try to make sure that we bond the number of classes both during the training and also inference to the classes that we are interested in highways. And also we had to use different data augmentation techniques to make sure that we are able to detect vehicles, let's say 500 feet before the work zone, or 100, 200 meters. And that's even we're going to go higher before it works on. But in many of those cases, you need to go higher resolution image processing, and higher resolution means more computation. You need to make sure that you can do the computation locally. So one thing that I forgot to mention is that we also see the trend toward edge computing, where rather than sending the videos to cloud or a remote server, you try to perform all required computation locally. And this is a clear example of that. First of all, you don't have that reliable connectivity to the cloud or a remote server. Many times in highways, cellular network is not that robust and reliable. Secondly, it's going to be significant delay, so you don't want to do that. So you have to do the computation locally, and by doing the computation locally, you're bonded with how much compute you can do. So you need to make sure that while you're achieving a state-of-the-art accuracy, in this case, I mean generally anybody that who wants to tackle this area, we need to make sure that also we can afford to compute that frame rate in real time. I guess I see a question here in the chat box. Let's see who is that. Uh,
Looks like if you could, I
yeah, I'm
guess
gonna be closer to microphone, but is it a common issue everybody has, or is just one person?
you're a little, you're clear on my end, but it's a little quiet. I think moving closer will solve the
Okay,
problem.
sure, sure. I could use my headset. Again, apologies. If please let me know if my voice is not clear. I can change that. I can use a headset quickly. Um, okay. Moving forward, again, I'm just going to give you an idea about our training approach in this case. So we use BDD 100K dataset, which has similar highway viewpoint as we are looking for, because many data sets, they don't have these highway viewpoints where we expect to see in a work zone, or where how we envision our technology to be installed, looking at the incoming traffic. So we are not interested in the bird's eye view, by the way, in this case. While one person can argue why not using drones to detecting incoming vehicles, I feel that yeah, sure, maybe, but it's not sustainable. You need to make sure that you can process information for, let's say, 10, 24 hours continuously. So I'm not sure drone can do that. So yeah, so we use BDD 100K. It's very interesting data set. I think it's quite unique. We couldn't find anything else. There's an overall shortage of data set in this domain with the perspective that we are looking for. But it has different views from San Francisco, Berkeley, Bay Area, and New York. And we nicely could identify the different vehicle type and classes, because this is very important for us finally for the risk assessment. Let's say we consider high risk for truck. Obviously we're not going to see training highways, but still we use that because that was part of the data set. And this is our results. And one thing that we did uniquely here, we evaluate our accuracy over three different distances. So let's say small objects, medium-sized objects, and large objects. And large is typically pretty standard. Let's say the one that you can see in other data sets like COCO or uh, open image from Google. But then we try to also go and identify vehicles that are further away, or even using data augmentation techniques to push back the vehicles and make them smaller and smaller, and use that in our training. So making sure that our network can detect vehicles that are further away. This is very important. And many times, again, if you look at the standard computer vision conferences or CVPR, they use the standard data sets. And one of the real world challenges that especially important in smart transportation is that how can I do distance classification and detection? Should I increase my resolution? It's going to be significantly, more computation. How can I find the right balance between data augmentation and my training approach? So hopefully I can have a good confidence of detecting and classifying vehicles from distance. Again, for the accuracy, we use mean average precision, which is a pretty standard for vehicle detection and classification. Overall, obviously for smaller objects, we have lower accuracy, but the quantitative number doesn't show everything. Qualitatively, we could see if we are pretty robust in detecting and localizing vehicles from distance as well. But obviously, as the objects are smaller, the displacements of the detection box going to be more pronounced. Therefore, you see a smaller relative MAP compared to larger objects. But on average, even 20% MAP for small objects is pretty good. I am not aware of any research that have done this level of accuracy measurement for different vehicle classes. I think the network that we propose and is under review, I think it's just received a minor revision, so it will be accepted hopefully soon. is near a state of the art or perhaps a state of the art on vehicle detection and classification. Uh, we uh, we also did a performance measurement and analysis. Again, it's very important. So for that one, we use NVIDIA Jetson platform, but you guys might be familiar with that, which is NVIDIA is leading tech on pushing the AI on the edge. And so overall, what we could see is that the FPS that we can afford would be 24, which is very good for what we are looking for if we run the board in a maximum power, which is 25 watts. And obviously, if you reduce the power budget to 7 watt, then your frame rate going to be 8 frames per second. So in this case, we need to meet 25 or 30 watt. That's what 30 frame per second. So this is what we are working on right now. But again, the power is pretty good. We believe that we can afford this power budget, especially if we can run the board on top of the track that they use for the highway work zone, so we can have a more permanent power. So we should able to afford 25-watt power consumption and reaching 30 frame per second. Um, these are some other qualitative results. One thing which is very important is the low light condition or night light. Um, and I mean, again, we try to make sure that in our training set, we have these kind of situations as well. And as you see in the bottom figures, that our approach is pretty solid in detecting the vehicles even during a low light situation, which is again very important in this scenario. However, we anticipate most of the short duration work zones do not happen during the low light situation, but still they may. So it's very important to have a robust algorithm. The other part that we're more excited is okay, you detect and classify the vehicle. So what? What do you want to do with that? And how can I relate that to something that leads to a risk assessment or provide uh, notification to the workers? In this case, we are taking some major leaps in doing vehicle trajectory analysis in highways. And this is not just limited or bounded to the high work zones. This can be used for a much broader range of safety related applications in highways because and crash prevention. Um, so again, I I'm just showing a basic graph of what we propose, and internally, we rather than just using traditional CNNs, we are using more dilated time convolutions and graph neural networks to understand and capture the dependencies between the vehicles because you cannot predict the trajectories in isolation. The trajectory of each vehicle depends on the trajectory of other vehicles, and you need to build, and a solid algorithm needs to able to build this relationship in real time and predict the future trajectories. So basically the input is, let's say, a target vehicle and past history of that vehicle and all other neighbor vehicles and past history of the neighbor vehicles. And the output is the prediction about the future path of this vehicle. Basically, that's a formulation of this problem that you can, again, generalize it for a broad range of smart transportation applications. And in this case, we are particularly interested in highway work zones. But there's no data for highway work zones. So the only way we could validate and see how robust is our algorithm was using a standard data sets that already provide that, and most of them are pretty old, which is, I was a little bit shocked, and we just find the US I-80 and US 101 that has been released with FHWA in 2005 and 2006. And even publications and papers you see in this year or last year, they're still using this data set. So clearly we need more label trajectory data sets of our highways. And if there is such a data available, I'm not aware of it, I would be more than happy you guys send it to us because this is one of the limitations that we have. But anyway, that's the data we used for training and evaluation of our algorithm. And a sampling rate of 10 hertz has been used, and we are analyzing vehicles over 45 minutes uh, uh, over the three different 15 minutes segmented traffic, different 15 minutes segmented classes of, you know, mild traffic or low traffic and congested traffic, because you also need to make sure that you're generalizing your trajectory prediction or your vehicle path prediction. It's very important. And these are some of the early results that we got. Again, just for the accuracy, again, we went with the standard measurement, RMSE, root mean square error, and when it comes to the future prediction, we are aiming to predict the next 5 seconds, which is significant in highways. And again, we are not the only one. There are some very interesting research have started in 2019, 2020, and even one in 2021 that tried to tackle a similar problem of vehicle path prediction in highways. Well, on the top, you see our accuracy numbers. We can beat most of the approaches, but there are two recent approaches that we are not able to beat them on the accuracy side, and this is something we are still working on. But what is very significant and very important is that none of these approaches have evaluated their capability for doing real-time path prediction in the field. And that's very important part of our research, and in general my research lab, is that hey, we are not just interested in the next cool algorithm, we are very interested to make sure that that's efficient enough that we can run it in embedded platforms on the edge on device processing. So the name of the approach is deep track, and we did some performance comparison. We see that I mean, the bottom table shows it. I'm not going to go to the detail of this due to the interest of time. That we are both on the model size and computation complexity more efficient. We also perform a real-time delay assessment on embedded platforms, and the delay of just processing this information and making a prediction is about 40 milliseconds, which is quite acceptable for us. Some qualitative results based on the model that I just formulated earlier, that green is the path trajectory. Sorry, red is the path trajectory, and green is the ground truth trajectory, real trajectory, and blue is the predicted trajectory. And please notice it's very difficult to present a qualitative result, because other vehicles, we are showing them stationary, but other vehicles are also moving. So we need to come with some creative ideas to present that in a better manner. But again, we did it pretty standard here as other approaches have done. And overall, we are quite happy for path prediction algorithm with the fact that we can run it in real time. And this has been very encouraging for us. But obviously, to achieve better results, we need more data, which I'm going to talk extensively about that at the end. I'm trying to go faster now. So another important part is this low latency, reliable communication between the camera and actually edge computing board and the actual workers. And obviously workers are not that happy and talking to each other. They're working in the work zone and distracted. So we need to make sure that we provide this real-time notification. So for that, what we did is quite a standard. I mean, we just need to make sure. So we decided to go with a Wi-Fi, and we decided to go rather than a peer-to-peer approach. We actually established a local Wi-Fi network with a router in the work zone. The reason is that because peer-to-peer not going to be scalable, and we decided to do the client-server model. In this case, the server is the embedded board, and the client are all these augmented devices, augmented reality devices or wearable devices. And you may end up to have multiple workers in the field, and you may want to notify them individually, and you have to, and maybe differently, depending on their position. So we decided to go with the server-client model rather than peer-to-peer model, and the communication protocol is pretty standard, but we just need to make sure that as we increase the distance, and the length of the work zones can be 100 meters, right, and more, even more, so still we have this reliable communication. And we know Wi-Fi are very susceptible to interferences, and we don't know what kind of crazy interferences we may have in our highway work zone. So we really need to measure and evaluate those. Again, we have done some real world measurements. So we actually created a small um, toy example of a work zone in our campus, basically, and establish this local Wi-Fi network, and then have the AI board, and then doing the processing and sending information to the augmented reality goggle, and then measuring the distance, measuring the latency of the uh, message passing, which is not going to be more than a kilobyte of information or a few hundred bytes. So the volume is not very important in this case. The important factor is latency. And we try to measure the latency even in 60 meter, which is pretty good. And granted, we need to go even up to 100 meters, and this is what we're working on. We observe at just 12 millisecond end-to-end latency, which on the worst case scenario, obviously, average is less than that. But again, it's a real-time system. We need to always consider worst case scenario. Again, these are part of our initial studies, but definitely we are very happy to see we are able to achieve low latency as needed for such a safety critical application. And this is very encouraging for us. Definitely the other aspect is that what if we have multiple users, and what would be the interferences of that, and what would be the impact of that if I have 10 workers, all of them wearing 10 augmented reality and other wearable devices, and I want to notify all of them at the same time, how does it impact my latency? The last but not least aspect of this research is real-time feedback to workers, that I'm going to stop sharing my screen, and my colleague Omi going to continue. Thank you.
Okay, thanks, Hamid, for going over the first two major steps of artificial intelligence for vehicle classification and the important trajectory prediction, and also the low latency communication. But then the next big question that we have is, what is the mechanism for feedback and notification? And that's pretty important because we couldn't find the prior work with a design framework for highway work zone workers who use an assisted reality or augmented reality glasses for this purpose. And there comes some very important questions regarding the interface. As you see, we needed to see what's the reaction of the users, or what are the user experiences to AR-based real-time, and what is the optimal user interface design for this context. In regards to user experience, we focus on some major questions, and these are common questions on user experience studies. We're interested to know what's the technology adaptation. Are they going to use, what's the pace of acceptance of this technology if it's used? We wanted to know what's the usability, how convenient and readable is this to the user? We want to know, is this practical? Are there majority of the workers that who think that this is not practical in the context of highway work zones? And we also want for them to be engaged. We don't want for some of them to feel like they're going to use it and they're not continuously being engaged and see the benefits of this communication. And of course, the user trust, and we're going to talk about the false alarms and those issues and the state of our future research. And also, we want to effectively and efficiently deliver the results from our AI and communication from the processing and the edge to our end users with a effectively designed interface. And also, we want to make it a best fit for the occupation of our workers. So for this purpose, two major things that I'm going to discuss is guiding you through a preliminary study that we did in user interface evaluation. One is the AR-based UI design and evaluation, and the other is the mixed analysis of the survey results. First, we started with defining the design guidelines. And those design guidelines are what color to use, what shape to use, where it's going to show up, is it going to be transparent, how much is the transparency, and many of these features. We needed to go to MUTC, other guidelines, and choose colors. Of course, this is our basic design, and the whole purpose of the process is to refine them, get feedback from the end users, and improve that. And then we started the expert group review. We recruited very experienced, one of them 20 years experience with DOTs and actively working as a maintenance crew to go through this panel for our initial design, then coming up with a mechanism to formalize the risk detection from the artificial intelligence. There are many factors, including the trajectory of the cars. There are many other factors that can contribute adversely to a work zone. And we want, the promise of this research is to proactively predict the intrusion of the cars before the intrusion actually happens, and how we want to do it fast, real time, and also give the best mechanism for that feedback. We designed at this step a low fidelity prototype. We were living in a pandemic year. We were very limited in approaching our community. And finally, we decided to do a multimodal UI design. I think briefly Hamid went through this. It has been proven that using multiple modes of notification is more effective. So we didn't decide to go only with auditory or vibration or textual and visual. And our final goal was based on using a multimodal. I think at this point, you already know that. The mechanism for the delivery of notification is a smart glasses. And for actually implementing this, we needed to go through many steps of which of these augmented reality or smart glasses we are going to use. Which one is a good fit for a work zone? Which one does have a safety requirement for that? So initially we decided to go with the model that you see here. It's a Vuzix, and as you see, I won't go through details one by one, but provides the basics that we need. It does have an embedded camera. It does have the ability to give auditory, visual, and vibration notices. So by using that, we got into the work of designing the interface that you see is going to show up in a transplant place that we see there. We decided that we're going to call the risk that is going to be imposed by the incoming traffic to the workers in a work zone as a risk factor. The mechanism for the risk factor calculation is going to bring a AI-based, data-driven. I think in the wrap-up, Hamid is going to talk a little about that, which is a future of this research. But assuming that we have that, we designed 4 preliminary design layouts for low, medium, high, and little risks at the highway work zones. And each one of these layouts on the top, let me see if I can better show this, low risk, medium risk, is going to show different risk bars, different types of notifications, and different colors or shapes to show the severity of notification and hopefully get a better response and reaction from the workers. So to this end, we started a survey and we provided some guidelines, including 2 videos that you see here. So if you really want to see the full videos, I don't think it's the best fit to play all the videos here. You can definitely go point to the QR code and take a look at these videos. One of them on left, which is this small one, is going to show you the fundamentals of what we did last year. And the one in the right is going to show you how the system actually works and some animation. But I would like to do is And my PhD student, Sepir, has narrated on this as a good source to get familiar or to spread the word to other researchers in the community about this. But I would really like what to do is to get in here and let me mute this because we don't want to play the whole thing. I'm going to go all the way to where we have an animation of intruding vehicles. It should be somewhere right in 220, right in here. So as you see, this work zone, let me play again. This is expected to be a representation of short duration work zone. And on the left and right, you see how the glasses, how it's going to be looked when you're looking through the glasses. This was one of our initial animations that we developed, and we have more realistic demos as of now, but I'm pretty confident that those transparencies and how the messages and notifications are going to show up are a good representation of what is the promise of this technology and augmented reality user interface design. Again, to take a look at a really fast 1 minute, 2 minute video of what's going on in regards to the research, feel free to point to the QR code and it's going to take you to those 2 videos. So the other thing that we did was a mixed method user research and analysis. We wanted to see what's the feedback of the end users and the actual users who are the workers. So we designed a survey and we distributed the survey to the highway maintenance and construction community. And we separated them to 2 groups, the ones that are actual end users, the workers, the maintenance crew, the construction crew who actually do the work are going to use this. And then second, the affiliated professionals or participants who are having a supervisory role, who are having some other roles, they're involved. They can provide us with insight. What we wanted to separate those results. So our survey is still live. So if there is anyone here who wants to contribute and add to what we have in survey, feel free to point. It's going to take you there. Our videos are going to be there and you're going to see how it's designed. Or if you're curious to see how actually the survey was, again, feel free to go ahead and you do not have to submit, So the steps that we did for this purpose was the initial qualitative user research through semi-structured interviews. We did a quantitative user research with all the closed questions that we had, and we did a usability test for early evaluation of the system, and finally a statistical analysis of the design. I also should acknowledge the support and help of Dr. Nicole Morris from University of Minnesota, she is our consultant on human factors, and she's a cognitive scientist, has been a great help in designing and going through these parts of our research study. So to summarize what happened in the participation, thanks to the engagement we got from North Carolina Department of Transportation, Virginia Department of Transportation, and DBI, our industry partner, we got 128 responses. It was real more than our expectation, and we're very happy about that. We got around 60% of maintenance crew, the ones that are actually on the work zone, and 40%, around 40% of the affiliated participants. We asked them to show us on which age group they are, and as you see, more than 50% were 45 years or older were present and the work zones. The other thing that we wanted to know, because we wanted to see how experience and age is impacting the adoption of technology and their willingness to go through this technology and actually use it or recommend it, we asked about the experience. 73% of our participants had 10 years or more of experience. And we can say, as you see, only 9% were between 0 and 2. So most of them had at least 90%, more than 90% had at least more than 2 years of experience. And finally, the most important one, were they actually present at the work zone or they were involved in other parts? We knew that we were sending the surveys to the highway work zone workers, but we wanted to double check and make sure that they're actually present at the work zone. As you see, around 90% of them are actually present at the work zones on daily or weekly basis with the distribution that you see here. We have done actually some statistical analysis on the results that we got. And of course, we had more questions. And that's the reason I encourage you to go through that link and see the actual survey for yourself. But I'm just going to visually represent four major questions and tell you about the results, and then wrap up the presentation. The first one was the practicality of the framework. And then again, maintenance crew and affiliated participants. As you see, more than half of our participants found it practical and very practical. And again, it was more than what we were expecting because this was a new one. Most of them never used an augmented reality glasses, not in this context, in no context, and 54% found it practical. And for maintenance crew, 32% they found it practical. Most of them were neutral about the practicality. I think at some extent it was expected, a new technology. They were not sure how to make decisions in responding to this questionnaire. The likelihood of using the framework, again, affiliated professionals, around half of them, they were found likely or very likely to use it. And that's good news. They're mostly open to use that. And the ones that are not willing or they find it very unlikely or unlikely, they're not that much. They're less than 20%. And this is another good sign for making the next steps in the progress. And I should put emphasis that this survey were based on our very initial run on our user interface, and we have done developments and improvements over that. Recommending to the others, again, half of affiliated professionals felt like they're going to recommend, but less of maintenance crew felt like they're going to recommend it. And again, less of maintenance crew actually felt that they're going to use that. And on first impression of the designed UI, as you see, 26% found it 26% of maintenance crew found it satisfactory or very satisfactory. It means that there is room for improvement and there is room to make it more intuitive for the workers, which are different. They're not actually representative on an average of our community or the users, and there needs to be more work from our end to improve that. The other thing that I wanted to summarize here was the participants' concerns about the proposed framework in general. This is not limited to the user interface. And I ranked them or sorted them based on the maintenance crew's number of comments. It means that 25 participants, for example, for first one, were concerned about unreliability of identifying dangers. And we should note that we didn't identify anything. This is just their perceptions. This is because our platform, we're not at a point to actually do this. We just asked them, how do you feel about this? And it shows that the perception and resistance of our audience, the maintenance crew, on the reliability of such technologies, or in general technology, I think that. And the second one, we were not surprised, the false alarms. And we feel like the workers have been using other tools or technologies that give more false alarms. Is it going to be like my fire alarm in my apartment that's going to go off, like, and it's almost never true, or I'm going to lose the trust? And we feel like this comes from the false alarms, and this is a generalization of other instances. And influence on performance, some of them are concerned if I wear that, is that going to be influencing my productivity? Is it going to obstruct my vision? And that's actually our concern too, how much of obstruction it's going to create. And that again goes back to our user interface design, which is good feedback. Impractical for highway work zones, we had less comments about that. And technology adaptation and pace of technology adaptation was the other one that we had. and unpleasant user experience with devices. I know we're running a little late, so I'm going to ask Ahmed to quickly talk about challenges, and then we're ready for questions and answers.
Sure, thanks, Omid. I'm going to be super brief. We identify three challenges. One is the data set. We need to create new data sets customized for hardware work zones. User acceptance, and you see many of the maintenance crew are neutral. They don't know. They are excited. They seems potentials, but they are really concerned about false alarm, privacy, reliability, or intrusiveness. And the things that we don't know, the problems that we know are easy problems. That what would be the adaptation considering legacy safety protocols and standards in the highways? What are the liability concerns if you really use this technology? These are the things that even social scientists need to be involved.
I think you got muted, Ahmed.
Oh, just the next slide, please. Yeah, the ongoing future, we are very excited with our ongoing collaboration with NYU and Semiha and Khan. Both of them are great colleagues, and we're excited that they have this virtual simulator of the highway work zones. We do see significant potential to creating a synthetic label data sets, and also doing experiments on the real, worker experience and understanding the perception and reaction time of the workers by combining augmented reality with virtual reality. That would be very cool experiments that we are looking forward to that. And obviously we are working in the industry to establish a real world hardware work zone to really test technology in a real world setting, and AI algorithms are data hungry. Assuming that we can fulfill the first requirement, we are really looking forward to build AI-based data-driven risk assessments for work zone intrusion. Thank you so much, everyone.
Okay, great. Thank you very much. This is a really interesting presentation. We have a few minutes, so I'd love to hear from the audience. If there are any questions, like I said, you can either use the Q&A button at the bottom of the Zoom screen, or you can raise your hand and I will unmute you and allow you to speak to the presenters today. In the meantime, I did have one question. You mentioned at the beginning that this research has all kinds of applications you envision to other smart transportation problems. Can you maybe give a high level of what you were thinking there in terms of applications to other smart transportation issues?
Yeah, 100%. I mean, Omid, you can elaborate on that as well. So what we believe is that not necessarily through augmented reality, but with the connected vehicles and past predictions, knowing the future trajectories of the nearby vehicles, how we can provide feedback or recommendations to manually driven or AI driven vehicles, right? So they can do the best decision on a spot. The other part is that for pedestrian safety, especially in a more city setting, that if you predict the trajectories, how we can provide feedback to the walkers or pedestrians, or this can be used for also law enforcement and public safety applications for sure.
Okay, and so since characteristics of work zones might vary quite a bit from work zone to work zone, again, understanding this technology is still in its rise. How do you envision that it might address work zones and roads of different shapes and sizes?
Ahmed, do you want to comment?
That's another. Go ahead, Ahmed, if you have.
Oh, go ahead. Yeah.
So that's a really good question, because when we go back at our NSF research study, we envisioned this to be for the short duration work zones, and that's absolutely true. We have several types of work zones: short term, short duration. We have work zones that are mobile and other type of work zone. We would love to extend the application that we envision for short duration work zones to the other type of work zones. Our immediate goal is to focus on short duration. Many benefits of trajectory prediction, user interface design, low latency communication, they're all applicable to those work zones, but maybe the placement, the arrangement and layout of our equipment might be different. If a work zone is very close to a curb, if a work zone is a short duration, and there are differences. And I think after setting up our test beds, we're going to have a better idea of how these things can play out.
What hardware or software enhancements are on the horizon that you imagine might improve the success of either the vehicle trajectory identification or of the maybe the workers' responses?
Software enhancers, that was the question.
Or hardware enhancements.
Yeah, I mean, this is basically what we try to create, the future advances, right? So hardware side, I believe that there are big tech companies that are taking significant leap to improving the hardware, but that's our job on the algorithm side to come with the agile algorithms they can learn over a small amount of data and provide more robust accuracy. And that's one of the future direction of this research that we're actually working on.
We
And the
have,
same goes for, go ahead.
we have a question from Daniel, who's actually working on the Work Zone VR project at NYU. As the UI becomes more multimodal, isn't there a concern for sensory overload?
That's a really good question. Like cognitive overload is one of the concerns when it comes to multiple messages. And that is actually one of the things that we are trying to measure. And this is a very timely question because we are about to go to Work Zone, and we have done all the arrangements to actually work with the workers on the job site and see their reactions to this type of notification systems. Our challenge is to find what's the optimal amount of load of notification that we can give them, and we have designed scenarios for that. Very good question, thanks.
Okay, so if there are no additional questions, I just want to extend a big thank you to our presenters, Professor Topke and Professor Shogli from UNC Charlotte. Really great hearing about your research today. Thank you everyone for attending, and check out our upcoming webinars, our Twitter page and our LinkedIn page. We'd love to have you in future events.
John, just one comment. I forgot to thank the students that are working in this project because this is the product of their work. Seper, who is here, and Reza and Vinit. Really great thank to them. Thank you so much for having us.
Thanks, everyone. Pleasure being here.
Yeah.
Take care.